Hello, thank you for watching this video. So in this video, we'll be doing question 10 of November 2023 question paper Physical Science paper 1. And this is the photoelectric effect. So question 10 reads as follows. Two spheres A and B made of zinc are at rest 0.1 meters apart on a wooden table. Sphere A is negatively charged and is free to move around on the table, while sphere B is uncharged and fixed to the table as shown in the diagram below. Let me try to read this thing again. Two spheres A and B made of pure zinc are at rest 0.1 meters apart on a wooden table. Sphere A is negatively charged and sphere A is negatively charged and is free to move around the table, while sphere B is uncharged and fixed to the table as shown in the diagram. So we have two spheres A and sphere B. Sphere A is negatively charged and is free to move on the table, and sphere B is uncharged and is fixed to the table. That is what is happening. So you can see your table, it's a wooden table there. I know the legs are not very symmetrical, but it's stable nonetheless. So let's continue. They are saying a high intensity ultraviolet light of frequency 2.8 times 10 to the 16 hertz is shown continuously on sphere B. So they are saying now a light of this frequency is shown on sphere B. Let's say this is the source of the light here. Source of the light of this frequency. It's emitting these photons there. So yeah, here is the light, ultraviolet light, so of this frequency. That is what is happening. So they are saying the work function of the zinc is 6.63 times 10 to the minus 19 joules. So we are told that the work function of zinc is what? 6.63 times 10 to the minus 19 joules. No problem. Then we go to 10.1.1. Then they are saying now, define the term work function of a metal. So they want you to define a work function of a metal. So as they said, it belongs to the metal, specific to the metal. So the work function is a metal property, right? It differs depending what metal you're dealing with. Like gold, from that of gold, it will be different from that of zinc, for example, or that of silver. So each metal have its own work function. So the work function is a property of a metal. But again, they're asking, what is the work function? So a work function, right, is the minimum energy an incident light need to have in order to emit electrons from a metal surface. So it's the minimum energy light incident need to have or requires to eject electrons from a metal surface. So we can say work function of a metal is the minimum energy, right, required or needed from light then to eject or emit electrons from a metal surface. So, like I said, work function is the minimum energy required from light incident to emit or eject electrons from a metal surface. Right? So, go to the next one. 10.1.2. What are they saying at 10.1.2? They're saying, explain using a suitable calculation. Explain using a suitable calculation why the ultraviolet light shown on a sphere B will eject electrons from its surface. So, they're saying now, this ultraviolet is shown on sphere B, right? They're saying use a calculation to explain why the electrons will be emitted from that metal. So, what we need to do, we need to calculate the energy of each photons. We need to calculate the energy of each photon, right? And compare that energy of each photon with the work function, right? Then if the work function is less than the energy of each carried by each photon, right? Then the electrons will be emitted. So let's go and do that. So the energy of a photon is equal to Planck's constant times the frequency. So you know Planck's constant is, so this is the electron energy of a UV photon is equal to Planck's constant, which is 6.63 times 10 to the 34 times the frequency, which is of the frequency of the incident light, which is 2.8 times 10 to the 16 hertz. So the energy of the ultraviolet light is equal to the answer of this thing. So let's patch that and see what it will be. So 6.63 times 10 to the minus 34 times 2.8 times 10 to the 16. You find that the energy of the ultraviolet light is 1.86 times 10 to the power minus 17 joules of energy, right? So you have the energy of the ultraviolet light to be what? 1.86 times 10 to the minus 17 joules. And then you have the work function, which is the energy needed to emit each electron from that metal, which is zinc, to be 6.63 times 10 to the minus 19 joules. So you need to compare these ones. So the easy way to compare them, subtract one by the other. If you say EV minus this, and the answer comes out positive, then EV is bigger. If it comes, say EV minus this and the answer comes negative, then EV is smaller. You know this. But because I know the energy of the ultraviolet light is greater than the work function, which means EV, energy of the ultraviolet light, is enough to eject electrons from a metal surface. This is what this means, because we said the work function is the minimum energy light incident need to have to eject electrons. Oh, actually, we said work function is the minimum energy required by the metal. So we said work function, which is the minimum energy required to emit electrons from a metal surface. So it's that minimum energy that you need to liberate electrons from a metal surface. So then now your light incident, or your incident light, which is ultraviolet light, have more than enough energy to free electrons from a metal surface. Because you can see the energy needed to free electrons is this one, and the energy of the photons is that, of each photon is that. So which means each photon have more than enough energy to release those electrons from that metal surface. Done. So because the energy of each photons of the ultraviolet light is greater than the energy that is needed, then electrons will be ejected. Done. Go to the next question. 10.1.3. What are they saying? They are saying now, sphere A carries a charge of negative 5.4 times 10 to the power minus 6 coulombs and requires a minimum force of 0.027 newtons to move from rest. Let me read this thing again. Sphere A carries a charge of negative 5.4 times 10 to the minus 6 coulombs and requires a minimum force of 0.027 newtons to move from rest. So now they're telling us now the charge of A is minus 5.4. 5.4 times 10 to the power minus 6 coulombs. That is the charge of the sphere A. It is that, right? And they're telling you, since they are sitting like this, a force, if we can have a force here of 0.027 newtons between the two spheres. If we can have a charge of 0.027 between the two spheres, this one, A, which is free to move, can move. Right? So if we can have just this magnitude of force between the two spheres, then sphere A would move. That's what they're telling us. They're telling us, let me repeat this again. They're telling us that A have this charge, which is negative charge, of course we knew. And then now they're saying this force, right? A minimum force of 0.027 newtons, right, will be enough to move A from rest. That's what they're telling us. Fine. They're saying now, calculate the minimum number of photons of ultraviolet light must strike sphere B, which will cause sphere A to move from its rest position. Let me read this again. Calculate the minimum number of photons, right, of ultraviolet light that must strike sphere B, which will cause sphere A to move from rest. So here's what will happen. Now, because we have this source of ultraviolet light that is shown to A, right, it has enough energy, which is that, to emit electrons from that metal. So electrons will be, many electrons will be ejected from that metal, right? They will be removed from this metal. So now, because it was uncharged, now you are removing negative charges, or removing negatively charged electrons, because you know that an electron charge is equal to -1.6 times 10 to the 19 coulomb, right? So if you are removing the electrons, you are removing these amount of charges from that metal. So now what would happen is, it's more like you will be left with a slightly positive version of the sphere, because you have removed the negative charges. And then now that negatively charged sphere now will start interacting with this one. Like, you know how charged particles interact. Electrostatics know that. Because now this one have an electric field around it, and this one will also have an electric field around it, which now will in turn, because this will be positive, it will attract this one to move towards it. That's what will happen, or that's what I think would happen at least. So now we know that these two have to interact, right? These two have to interact such that this one moves or is attracted to that one. So we know the electrostatic force between them. The minimum electrostatic force required for this one to move is this one here. That's what they told us. So we can find the magnitude of this charge here and see how much electrons were removed from it. Or find the total charge of electrons removed from it. Then that will in turn tell us how many electrons were removed, and that number of electrons will be the same as the number of photons, because each photon is responsible for removing one electron. So if you know how many electrons were removed, then you know how many photons were there. So let me explain my strategy again. So we have the electrostatic force. We need a minimum electrostatic force of 0.02 newtons in order for this one to start moving towards this one. Right? No problem. Then, now, what I'm saying now, we need to find the magnitude of this charge. It will be positively charged, right? Then we will know how much, what is the charge removed from this one, because if this one was neutral, it had no charge. So if it is positive, then the amount of charge removed will be the negative of it. Right? Then once you get that, you can find how many electrons were removed. Once you find how many electrons were removed, then you can find the number. Once you know how many electrons were removed, you will know you will know how much photons were incident to our light, were incident to our metal, because each photon is responsible for removing each electron. So let's go. So say the electrostatic force is equal to K, Q1, Q2, all over R squared. This is Coulomb, you know it. So we know the electrostatic force to be what? So we can say if you're A, B. The electrostatic force is 0.02, right? 7 newtons is equal to K, which is 9 times 10 to the 9. Q1, which is 5.4 times 10 to the -6 times the charge of B, all over the distance between them, which is 0.1 all squared. Then solve for that. So you say your QB is equal to 0.027. You know how to solve. Times 0.1 all squared, all divided by 9 times 10 to the 9, 5.4 times 10 to the -6. So the charge B is equal to 0.027 times 0.1 squared, 9 times 10 to the 9 times 5.4 times 10 to the -6. So the charge of B is positive 5.56 times 10 to the -9 Coulomb. Right? Which means the removed charge due to those electrons is equal to -5.56 times 10 to the -9 Coulomb. This is the removed charge. Then now the next question is, how many electrons were removed that are responsible for this amount of charge? How many electrons were removed that were responsible for this amount of charge? So you say, okay, I know that a number of electrons were removed with this charge, and this charge was adding up to that Q removed there. So the number of electrons were removed. This is the number of electrons removed. They had this charge 1.6 times 10 to the -19 Coulomb is equal to this total number of charges, total number of electrons had a total charge of that, which is -5.56 times 10 to the -9. So the number of electrons removed, right? Number of electrons removed, number of electrons removed is equal to this thing divided by an electron charge, which is 1.6 times 10 to the power minus 19 coulomb, which is 3.47 times 10 to the 10 electrons were removed. But you know that each of these electrons was removed by one photon. So if you had this total number of electrons removed, which means you had this total number of photons entering the things or hitting our metal. So we can say therefore the number of photons is also 3.47 times 10 to the 10 to the 10 to the 10 to the power 10. So this is the total number of photons, because if you had this number of electrons removed, each one of them was removed by one photon. So there's a 1-to-1 ratio between the number of photons and the number of electrons and the number of photons. Therefore, the number of photons will also be this one. Done. So I'm going to clean the board and then we do this spectrum stuff. So let me clean the board. Okay, so now we are doing 10.2. Just saying, a beam of white light is shone through a cold gas. The emerging light is dispersed and the line spectrum is observed on a screen. Let me read this thing again. 10.2. A beam of white light is shone through a cold gas and the emerging light is dispersed and a line spectrum is observed on a screen. No problem. 10.2.1. So here is what they are saying, right? They say you have this, let's say this is the source of white light. White light, for example, let's say sun, because white light is basically light similar to that of the sun. You know how the sun looks like? No, that is white light. So it's passed through a cold gas. This is a cold gas here. So this beam of light is shown into this cold gas here. And then at the back, you observe some sort of absorptions or some sort of line spectrum. That's what they're telling you. So you have your spectrum here. So which means your line spectrum down here. So here is it, of whatever that comes out of it. That's what they are saying. That statement that says a beam of white light is shown through a cold gas. The imaging light is dispersed and the line spectrum is observed on the screen. So let's go to 10.2.1. Name the type of the line spectrum observed. So the type of the line spectrum observed is the absorption spectrum. Fine. Go to the next question. It's the absorption spectrum. You might be wondering, what is an absorption spectrum, right? Which is what we're going to. 10.2.2. Describe the spectrum observed in 10.2.1. So what is an absorption spectrum? Describe this spectrum that you can see here. We said this is an absorption spectrum. So describe the spectrum, right? I'll describe the entire thing and then, but let's go. So first, what is absorption spectrum? So you can have a continuous spectrum. In this case, if it's a white light, where you have your full complete range of wavelengths from your indigo to, actually, from your violet to red, which is from your shortest wavelength to your longest wavelength, which means here you'll have your violet, maybe. Here you'll have your red, which is from your shortest wavelength to your longest wavelength. So you can have a wide range of the spectrum of that. You can have an absorption spectrum, you can have an emission spectrum. But in this case, we have absorption. So let's stick to this one. So they wanted to describe this spectrum there. So just for your own benefit, what I'll do, I'll first describe what an absorption spectrum is. I'll first define it. So I'll say an absorption spectrum, right? It is the type of spectrum that is observed when a range of electromagnetic wavelengths are passed through a substance, or maybe a gas, as in this case, and some specific frequencies are absorbed by the gas, and they are shown on the spectrum as black lines, because all other frequencies pass through, but the absorbed one will appear as black lines at those specific frequencies. So they want us to describe this as 2 marks. They want us to describe this line spectrum. So this line spectrum will contain all other wavelengths, right? Will contain all other wavelengths except for the specific wavelengths that are absorbed. And those specific wavelengths that are absorbed will appear as black lines on the line spectrum. That's what happens. So I'm not sure if I have to write that down, but I'll start by defining this and saying now, absorption spectrum is the type of spectrum observed when electromagnetic wavelengths I'll say observed when a range of electromagnetic wavelengths are passed through a substance or gas, as in our case up there, and specific wavelengths are absorbed by the substance or gas in our situation. Right? Now I'm going to describe the line spectrum. So the line spectrum appears containing black lines, right? So black lines, the black lines at specific wavelength that were absorbed by the substance. So the spectrum will appear containing black lines, a specific wavelength that were absorbed by our substance. Done. This is how I would describe it. So let's go to 10.2.3. Okay, so now we're doing 10.2.3. 10.2.3 read as follows. The diagrams below, which is A and B, indicate some possible energy transitions made by atoms. Which one of the following diagrams could result in type of spectrum that is observed in 10.2.1? Diagram A or diagram B? So, okay, these two diagrams that you see here, they are showing possible energy transitions made by atoms when this experiment was made. These two diagrams, A and B, they show us the possible energy transition that might have been made by atoms within this gas when this experiment was carried out. So we said a light was shown into a gas and we observed a light spectrum. I said that light spectrum is an absorption spectrum, right? Because some certain wavelengths were absorbed by the gas, right? So those wavelengths that were absorbed on that gas, they were absorbed by atoms within that gas. They were absorbed by atoms within that gas. That's what happened. Which is why we have the black lines. The black lines that we see there are indicative of those missing wavelengths that have been consumed by our atoms, or that have been used by our atoms, or gained by our atoms. No problem. So if you are that atom, you have gained energy, right? Which means this white light contains those frequencies, right? All those different wavelengths from your red to your violet. So if you absorb those wavelengths, which is you absorb some energy, you are gaining energy. So if you're looking at this one, you can see that this one has dropped down. The energy decreased from here to there, decreased here from here. But if you look here, the energy from here to there it increased. The energy from there increased. So the energy has been absorbed there. Specific energies of that white light have been absorbed, which means the energy have increased. The energy of those atoms have increased because those energy have gained some energy, which means our electrons, I would say they are more or less excited. So I'll say diagram B. I'll say this diagram B, which is this one here. I'll say it's the one that is indicative of possible energy transition made by the atoms of this gas, because they have absorbed energy, so which is they'll gain energy and go up the energy levels. They're excited. So that's how I would approach it. I'm not sure if it does make sense, but I hope it does make sense to you as it does to me. Thank you for watching. Cheers.